Let's figure out the magnetic field of a bar magnet at an axial point. So this is say your north, this is say your south, and this is your axial point. If I have to keep a imaginary north monopole over here, so it will experience what? It will experience a push which is lot more than the pull. Reason being, in this case the north is near, that's all, nothing else, nothing fancy. Okay. The point is how much amount of push and how much amount of pull, what is the net force? This is what we are looking at. So we'll consider, let's consider bar magnet with magnetic length. This is say L, this is L, this is our center. This is south, this is north. Dipole moment is M actually. Let's not use this. Let P, and the direction is from south to north. Let P be a point on the axial line. This is our axial line at a distance of R from the center O of the magnet. Now we have a push and we have a pull. Push is because of the north and pull is because of the south. So first thing first, what is the force that the north end will apply? So it will be mu naught by 4 pi qm divided by r. This will be r minus L. This length from here till here, it is r minus L. So this will be r minus L the whole square. Right? Then it is in the direction of the, say I'll take it as I cap, in the positive direction of your x-axis. So considering the magnet is along x-axis. Next we have the south to be equal to mu naught by 4, not 4 pi, 4 pi qm by, this will be L units more, further in this case, not more, further, R plus L. And this will be in the negative direction. And so therefore your field, the net field at point P is given by the sum of these two. Simple superposition theorem. So when you substitute, 1 by 4 pi is going to be common. Qm is also common. And we're left out with 1 by r minus L the whole square. And this is minus 1 by r plus L the whole square, pointing in the direction of I. A bit of math over here. So LCM and all of that, square and everything. So we end up with r plus L the whole square minus r minus L the whole square. So that will result in 4RL. This is because of, I'll explain that, divided by, this is r minus 1 into r plus 1, r square minus L square, a square minus b square formula, the whole square. Again, this is not needed for your exam, what I'm going to write now. So this is as per a square minus b square formula. Of course, the whole square is not because of that. There is already a whole square. And in the numerator, it is because of a plus b the whole square minus a minus b the whole square. So when you expand it, a square and b square gets cancelled and we left out with 2ab plus 2ab. And so we end up with this formula. Okay, yes. End up with this result actually, not formula. And now, what can we do with this? we always have to express in terms of moment. So dipole moment is Q m times of 2L pointing in the I direction. Okay, here there is I as well. So all in all, we can write Q 2L I cap as m. So our force, or in this case axial, will be equal to the constant. Then this will be m, r will be remaining, how far it is, r square minus L square. And that's it. Your directional and every aspect is covered. So this we are handling direction as well. So we have a special case wherein we have the point to be far, far away from the dipole. In this case, the formula will be mu naught by 4 pi m r by, there's a square actually, r by r square, the whole square. So this will be r cube. So similar pattern we have seen in our dipole with elliptical phenomena. Right, guys? So now it's time for you guys to pause and have a look. So all we did was look at the force at the pole, added them. That's it, nothing else. Oh no, I have missed a 2, guys, over here. Sorry. So there is a 2 also. And here we have a 2. And this is how they're representing. So let's stick to that. Let me change this as square. Okay, this is your final answer.